When observing a system evolving randomly over time, the motion often appears too erratic to map. Tracking every sudden shift seems to defy mathematical structure. We typically begin to organize this chaos by defining its container, the domain of the time parameter, and the space where the states exist. We might look at people entering a room as a discrete process observed at set intervals. Conversely, we could track the exact unbroken concentration of gas emissions as a continuous process in continuous time. These categories provide the necessary framework for our data, but the true analytical nature of a stochastic process is found in the probabilistic rules that govern its internal evolution. Identifying whether a process is discrete or continuous is the first step, but it does not tell us how a system's future state connects to its past history. For that level of detail, we have to look deeper into the mechanics of the variables themselves. To dissect these internal rules, we will use a foundational model from our source material, tracking the accumulated number of heads, which we will call x sub n, after a series of fair coin tosses. This model operates in discrete time, with a state space that jumps between whole numbers from 0 to infinity. The engine of the model is the variable y sub n. If a toss results in heads, y sub n is 1. If it results in tails, it is 0. The state of our accumulation, xn, is the previous total plus the most recent toss, expressed as xn equals xn minus 1 plus yn. Every y variable is independent and identically distributed. Each flip carries a 50% probability, regardless of the previous step. This cumulative equation allows us to test three universal properties that define the behavior of random evolution. The first analytical lens involves examining the behavior of a system's jumps over a specific interval of time. Mathematically, an increment is the total change in the observed characteristic between 2 points in time. In continuous time, this is written as the difference between 2 points on the curve. In our discrete model, the increment is simply xn minus 1. A process has independent increments if the outcomes in disjoint, or non-overlapping, time intervals have no effect on each other's probabilities. We can apply this to our coin toss model. On the left, we've isolated two disconnected jumps in the sequence. By subtracting the previous total from the current one, we find that the increment is exactly equal to the value of a single coin flip, yn. Since we defined every coin toss as an independent event, the resulting increments are, by extension, independent of one another. The model passes the first test. It has independent increments, meaning a spike in one interval provides no information about the probability of a spike in the next. The second analytical lens tests the relationship between the system's future and its historical past. A Markov process is a system where the probability of future behavior depends exclusively on the present state. In these processes, historical data is mathematically redundant. When the Markov property exists in a continuous time and space container, the system is described as a diffusion process. This physical phenomenon was notably observed by Albert Einstein in 1905 as he analyzed the random movement of particles suspended in a fluid. The formal mathematical foundation for these observations was later developed by Norbert Wiener, leading to what we now call the Wiener process. We can prove our discrete model is also Markovian by examining its conditional probability. This equation represents the probability of reaching a future state, conditioned on the entire history of every flip that came before it. We can rewrite this by substituting our variables with the difference between states. This focuses the equation on the increments rather than the total count. Because each jump is simply the result of a coin toss, we can isolate the independent y variables. Since the tosses are independent, the previous results have no impact on the current one. The mathematical history of the process effectively zeroes out. This leaves us with a simplified result. The probability of the future state depends only on the state immediately preceding it. With the history collapsed, the system is proven to be strictly Markovian. It is a process without a memory. The final lens is stationarity, which determines if the underlying rules governing the system change as the process moves forward in time. We distinguish between two types, strict stationarity and stationary increments. Strict stationarity requires the entire joint probability distribution of the process to remain the same, even if the whole timeline is shifted forward. A process with stationary increments has a more flexible requirement. Intervals of the same length must share the same probability distribution, regardless of when they occur. To test this in our model, we can isolate a single jump occurring in the present. If we move that same observation window into the future, we are looking at a new increment. Both of these jumps are driven by the individual coin toss variables, yn and yn plus m. Because the probability of a head is always 50%, the probabilistic distribution inside both boxes is identical. This proves our model has stationary increments. The passage of time does not alter the system's internal rules of evolution. The seemingly erratic behavior of a stochastic process, no matter how chaotic it may appear on the surface, often contains a rigid mathematical structure. By applying these three lenses to our coin toss model, we have identified its core internal characteristics. We confirmed the model operates with independent increments. We demonstrated that the system is memoryless, satisfying the Markov property, and we proved that the process operates under stationary increments. These three properties were generated simply by ensuring that each individual step in the process was independent and identically distributed. Analyzing a stochastic process begins with its container, but its predictive power is found in these underlying probabilistic characteristics. Measuring independence, memory, and stationarity reveals the internal mechanics that dictate how a random system moves from one state to the next. Defining these specific metrics provides the framework needed to model future outcomes based solely on the data available in the present.